a very, very good teacher, first of all. So he explains concepts in physics really well, and he has many years of experience teaching a lot of different students right now. And he's also a physics instructor at an institute in Bangalore called Gate IIT. So, welcome, Alan, and we are happy to have this workshop running today. It was really nice to just plan it in just around a few days' time, and we wanted to address this topic. We've addressed a lot of the other topics like astrophysics and cosmology before, but we had not created a workshop or a course for quantum mechanics. And instead of making it just a 40-minute talk where only he's talking and you maybe get like an intro of it, instead of that, we wanted to design something a little bit more rigorous. So this is going to be very, very interactive. As you can see, he has a lot of different topics planned out. So please be a part of the conversation. You can always raise your hands. I'll either call out your name or Jivan will call out your name, and we'll be able to unmute you as well. So you can just be a part of the discussion. You can also leave your question in the chat box if you'd like to. So we are just going to wait for another minute and then we are going to get this started. And like I said, there is going to be a quiz at the beginning. So we'll ask Alan to talk a little bit more about what he wants to cover today. So all of you are kind of prepared for what is to come in the next couple of hours. And after that, we will have a quiz. It's basically going to be on a website called Quizzes. Some of you might have already been a part of our live quizzes before, but we'll just give you a code, and it's a very simple process. You just have to go to the website, put in the code, and you'll be part of the live quiz. So yeah, we'll give you a tour of that in a minute. So I think just before we get started, Alan, is it okay if I just share my screen for a minute?
Yes, yes. I'll just stop the sharing.
Okay, I hope you can see my screen. So I just wanted to quickly show you, since we are waiting for a couple of more people to join. So some of you are really new to Nakshatra, and I think you're probably coming to our event for the first time. So just to give you a little bit of background, Nakshatra has been around for just around 8 to 9 months now. We started at the beginning of this year in January, and we actually started as a community of people interested in astrophysics, cosmology, and basically physics-related subjects. So right now we are looking at a much more diverse, multidisciplinary community where people with different various, academic interests can come together and work on projects. So we also offer courses where you get to learn from experts. Like for example, today we have Alan, and this is our website. You can go to learn.nakshatra.com, and the four basic you can say four basic pillars of what we offer is, the first is mentorship. So I think, I come from an engineering background, and I was very, very interested in physics, and I didn't have mentors with me early on. So it was very important, I think, for everyone here to have an expert who can sit down and have a normal conversation with you. So we make sure that we bring those people on board. And secondly, crowd collaboration and peer-to-peer learning. This is a very exciting aspect of what we do, because we allow people to just, talk and get to know strangers from around the country or around the world. And you just get together and work on a project. Right now we have like these free projects running on our Discord server. Jivan will put the Discord link on the chat box. So we have a project on dark matter going on, and then there is like a Python coders project as well going on. So there are always a lot of activities where there is emphasis on collaboration between people. You don't always need like a professor with you or whatever to guide you in a project. Most of the times, it's just it's a fun thing if you can just implement a couple of things you already know about. And that's where implementation comes in. So we are not just going to teach you a bunch of topics or concepts, but we really want you to be a part of that research experience. Go out and dig technical papers and figure out the core part of that particular subject on your own. So which is why it's really important to, number one, ask questions, and number two, figure out how to tackle them as well. So I think problem solving is a huge thing that we try to address in our courses. And fourth is knowledge transfer. If you're someone who's kind of finished masters, or you just have a subject of expertise, you can always come on board and just tell us, hey, I would like to give a talk for an hour, or I would just like to address the crowd. And we are really open to exchange of ideas and exchange of knowledge. And we have a bunch of clubs that anyone can be a part of. We have a reading club, a writing club, which people write on our blog. You can go check out our blog here. We have a coding club. So it's like a virtual campus basically, and you have the freedom to even start something of your own. We are a student based organization, so we are always very open to suggestions from everyone here. And yeah, you can scroll down and you will find a bunch of courses. This is a very very new platform, so please, we apologize for if you find any technical difficulties. But basically you can just go and apply for any of the programs. Equilibrium is something which Alan here, who's going to be speaking today, he is going to be the speaker, the mentor for that entire course. And it's a 6-week program on classical mechanics, and I think today it will become apparent how important classical mechanics is in order to learn more complex subjects as well. So this is something we are starting hopefully in the next 1 week, so a week and a half maybe. So please make sure you go here and apply. So I'll speak about programs maybe when we take a break in the middle of the session. So I'm going to stop my rant now, um, and we'll probably Alan, can you talk a little bit more about what you hope to cover today?
Yeah. Okay, so I suppose you all can see me.
Yeah, yeah.
Okay. So, students, this is a workshop on quantum mechanics. All right. What we came to see is that quantum mechanics is a fairly new topic for a lot of you students. It's a topic that is introduced in the third year of your undergraduate course, and many students who are pursuing or want to pursue or plan to pursue physics or mathematics later on in their lives, in their careers, uh, the quantum mechanics becomes a very integral part of your career, so of your education. You can see that in this course, I'll be covering about the entirety of quantum mechanics. We have tried to summarize the entire topic in a way that we can finish it within 2 hours. We are going to start with understanding what quantum mechanics is and what was the need to shift from classical physics to this new version of physics, the quantum physics. And I'm going to also tell you about what is the grounding principle using which we study or we perform quantum mechanical research. You're going to understand what part or what aspect of theoretical physics is used in quantum mechanics. Then we are going to go through the Schrodinger's methods, the equations that he had created, and basically that becomes the starting point of quantum mechanics. We are going to talk about one very important interpretation of Schrodinger's equation, which is the Max-Born interpretation or approximation. After that, we are going to talk about one another important topic here, which is the operators and the operator algebra. I'm going to talk to you all about the expectation values, what is meant by the expectation values. Right after we finish that, we are going to take a short break in which I'm going to address some questions of yours, and you're also going to go through some questions, some pre-written questions that we have put on the quizzes. So after you go through it, then I'm going to take it to a little higher level in which we are going to introduce a higher level of mathematics, which is popularly called as Dirac's approach or Dirac's matrix mechanics, in which we are going to see what that is about. And I'm also going to introduce you to a lot of new other methods as well, using which you can study quantum mechanics. You will come to realize that quantum mechanics is not as complicated as the popular crowd makes it sound like. It's not as such. We're going to talk about some applications. We cannot obviously cover everything. in as far as the applications of QM is considered. So we're going to talk about as many applications as we can. And just as an example, to end the session with a little bit of curiosity, I'm going to give you an overview of what is meant by quantum tunneling. So, of course, it would be great if you can just go through the quizzes before we start. I think Jeevan and Sitara would introduce you about that. And once you all are done, we can start with the course. So that's it, Sitara.
Yeah, so I think you guys can see the quiz link on your chat. So Jeevan, can you unmute and just lead them through the process?
Sure. You just have to click on the link, nothing else, and the quiz will automatically start. So once all of you have joined, I see that a lot of people have joined already. Once all of you have joined, I'll start the quiz. So Alan, do you want to explain after each question, or do you want to take it to the after the quiz is over?
No, I think we start once we get the heads of that quiz part is finished.
I think we can see 18 people, so there are probably 38 of you here on the call. So please just click on the link. You don't really have to do anything else.
We have 24 people who have joined the quiz. Is there anyone else joining? Can you type in the chat? We can wait for it.
Yeah, if no one else is joining, we can kind of start the quiz. Yeah, I think we can get started. So the reason we want you guys to kind of try the quiz out is because it's really relevant to what he's going to teach, and it'll give you a full idea about what you can expect to learn today. So we'll just give you another 30 seconds in case you want to join. Yeah, you can start, Jim.
Okay, starting.
I think for those of you who are not participating in the quiz, it might be fun to see someone play it. So maybe Jeevan, you can share the screen so that the questions are appearing at least.
Okay.
Yeah.
Could you like send the quiz link again, please? Sorry, I was a little late.
So there's actually a time limit, so you should ideally try to answer it within 20 seconds.
So Akash is leading currently. This question has multiple answers, I think. So you select all that is correct. Okay, last two questions are subjective. So just type out your answer. Please type your answer and submit. Okay.
Yeah, this is a funny answer. Niels, what
Yeah,
happens?
it's a funny answer. Extra points. Okay, last 10 seconds. Okay, one last question. Hey, I think the
Yeah, produced as errors.
uh, are you guys seeing the full question? It's in the end it should be produced
As a result of the
as a
time travel.
result of
The
time
time
travel.
travel. Yeah.
Just add as a result of time travel in the end. How would we avoid errors in the laws of physics that could be produced as a result of time travel? Okay, last 20 seconds.
These are some really interesting answers. Is there a way to copy them and like save it or something? Jim?
Yeah, yeah, they will be saved.
Okay.
We'll be addressing these questions at the end of the seminar.
Okay,
So it's done. Oh, can you share the results with everyone?
just a minute. Yeah, sure. Yeah, so herein is number one, Akash second place, Anirudh third place.
Noteworthy mentions Yash and Vinayaka. All
Yeah,
right.
most of you got more than 50%, I think. Cool.
All right, then I think we should start now.
Yeah.
Okay. So coming to the screen share. All right, students, as I've told before, the entire program will deal with quantum mechanics. It will explain almost everything that you would be studying in your degree courses and a little bit of what you're going to study in your postgrad courses. I'll just go through the topics once again. We're going to start with the understanding why quantum mechanics is important. What was the need of starting all this when we already had a lot of topics in classical physics? And one very important tool in theoretical physics, see, you will come to understand later that quantum mechanics started as an experimental science. It was to explain a lot of it phenomena that we were seeing, and what it came to become later on was a branch of pure theoretical physics, and it uses the entire quantum mechanics revolves around one single topic which all of you are familiar with, regardless of whichever level you're coming from, whichever class you're coming from. That is energy. All right, so we'll talk a lot about that as well. Then after that, I'm going to explain to you about what is Schrodinger's equation, what are Schrodinger's equations, and what are the wave functions and everything, and how are they important in quantum mechanics. And there are two understandings about about wave functions or Schrodinger's equation that you will come across. The first is the statistical interpretation, which is also called Born's interpretation, after Max Born, the guy who gave that. And the other one is the operator or the operator algebra. So we'll talk about that as well. And once that is done, the last part of that first part would be to understand what is meant by expectation values. All right, what do you expect as a result of an experiment, or in other words, theoretical experiment? What would you expect? After that, we are going to talk. We're going to have a short break in which I'm going to address your doubts and some questions, and then I have put some of my own questions for you all that I want you to give a thought about. It's you're not you don't have to give answers to all that. You can just make note of that, and you can think it yourself later. Most of these questions I'll be addressing in the second part itself. So the second part will include Dirac's matrix approach, matrix mechanisms. So we'll talk about that, and then some applications of quantum mechanics, which is also very important. And in the last part of this will be a short description of one very interesting topic, which is sort of very popular, as a matter of fact, the quantum tunneling. It's popular in in the undergrad and preschool level. So we'll talk about that. So starting the course, we are going to understand what is meant by quantum mechanics and why was there a need to use quantum mechanics. A very simple understanding. Take a look here. When we talk about physics, what do we study? What do we ever study whenever we talk about physics? We always talk about trying to explain the events that occur in nature. Isn't it so? Over time, over a period of a lot of years, 500, 600 years, we have come to realize that whatever happens in our universe, not just on our planet, in the entire universe, happens according to or based on some very important laws. Now, these laws are not created by us, these laws are not made by us. Newton did not create their laws. These laws were just discovered and understood by us. All right, these are called the laws of physics. And according to our understanding, these laws of physics can never be disobeyed. This is how the universe works. It's a simple harmony with a lot of complicated structures according to which every single event occurs. Whether you talk about tossing of a coin, even if you talk about waking up, what time you wake up, to topics as complicated as formation of a black hole or the birth of a universe. Everything is supposed to occur according to some laws. So, how do we do that? From here, physics divides into roughly two parts. The first we normally like to call macroscopic physics, in which we talk about the macroscopic world as big as it can be. We talk about us, we talk about objects, we talk about a body moving from a point A to a point B. Then we talk about planets, we talk about celestial bodies, we talk about stars, galaxies, the entire cosmological stuff. The other one, which is a little smaller, is microscopic physics. Microscopic physics. So, what do we talk about here? We talk about matter. We talk about materials. When you look around yourself, you see a number of type of materials. Now, this might be a little familiar with chemistry. So, what happens here? When you talk about materials, there is one simple question, one very simple question that comes to all of your mind, whether or not you want to answer it. What is matter made of? The first very dominant answer to this question was given by Dalton in his atomic theory. And that itself was the birth of a very interesting field in physics. What is this atom? You all know that atom can explain everything, isn't it? So it can explain all the physical behavior, it can explain all the chemical nature, it can explain every type of interaction of one material particle with another material particle at smaller levels, right? So the question was, how do we understand the structure and the function of this atom? Now, this was a very intriguing question, even till date. This is a very intriguing question. If I ask any one of you, why is it that metals are conducting but non-metals are not? There is a simple answer to this today, because you will tell that, okay, conductors have high conductivity and insulators or non-conductors have poor conductivity. If you go, if you are a degree student, you would answer it as the energy gap between the valence band and the conduction band in conductors is very less to zero, and in non-metals it is very high, fairly high. The point is that there are a number of answers. Now, we came to understand that if we studied this topic using classical mechanics, using classical physics, as in your mechanics and electromagnetic theory, these two came out as incomplete. I wouldn't say it was useless, but it was incomplete in the sense that it was not able to explain the answers to the questions here. And what was the reason for this? The reason was that particles as small as an atom and particles even smaller than the atom were behaving in a very weird fashion. Now, you or I or anyone have never come across a particle that has a potential to behave neither as matter nor as wave. And here I would like to tell you all what is matter and what is wave. There are a number of properties about matter and there are a number of properties about wave. The first and foremost is that matter has momentum. It has momentum using which it can exert and experience forces. Isn't it so? Any type of any form of matter you talk about, literally any form of matter, it will always carry some momentum because of which it can exert a force because momentum can change and it can experience a force, right? Waves do not have any momentum. Waves produce the effects. They produce the effects. Effects of what? They produce effects of vibration. They produce the effects on increase or decrease of temperature. They produce the effects of luminosity. There are obviously many forms of waves. Principally, they are dealing with vibration of matter and vibration of fields, electrostatic fields and electromagnetic fields. Now, the particles that we are dealing with here in the microscopic world are weird in the sense that they are behaving both as matter and waves. So they have momentum, but they are also capable of producing effects. Now you can see matter has momentum. So what does wave have? Waves naturally carry a frequency and they actually carry a sort of or a level of energy. Which type of energy? Kinetic energy associated with it. So if let's say you were an object and you were to absorb or experience a wave, you would start to move automatically. The best way to understand what a wave would be is that if you keep an object on the table, all right, for example, your laptop right now. Now, suddenly imagine that your laptop starts to move, and it's a typical motion in which it starts to move to and fro. It starts to oscillate to and fro. So, in such a case, if the particle or if this body starts to move without any reason, then you will know that there is a wave that has produced this effect on this body, and because of which it is moving. That is what a wave is. Now, these particles behave both as matter and as waves. So, classical mechanics was unable to give answers to this. So, what did we do? Typically, going again to the atom, many experiments proved us that one of the principal constituents of the atom, which is the electrons, are not just particles, they are particles that can behave as waves. And there was another theory that showed that electrons are waves that can behave as particles. I'm referring to two very important theorems of this time, of the 20th century, the Compton effect and the de Broglie's wave hypothesis. We came to understand with a number of different experiments, a number of different observations at the onset of the 20th century and the late 19th century. There were a number of experiments that were performed by very prominent names of that time. All right, people that we, what's it called, study about even today. Now, they performed a lot of experiments that created a lot of confusions and a lot of questions about the atom and every particle smaller than the atom, the electrons, the nucleons, that is the protons and the neutrons, and even one very interesting concept about photons, which was given by Planck and then later by Einstein, the quantum particle, or just a small packet of energy which is present in electromagnetic waves. Any type of electromagnetic waves, principally light, is actually made of small, small particles or small, small packets of energy. Of course, you know by now that wave is nothing but a packet of energy, kinetic energy here. So we came to realize that electromagnetic waves are also nothing but packet of energy, but they are not just a single packet of energy. They are a collection of many packets of energy, and each packet of energy there is called a photon. So a number of questions came to occur. What were the questions? The result of the Compton scattering or the Compton effect proved or actually confirmed two very interesting results. First is that photons can behave as particles. So, what was Compton effect actually? A Compton effect or Compton scattering, as some books would say, was a phenomena in which you have a photon, which is principally a wave. And please remember, waves can be absorbed, they can be transmitted, they can be reflected. At that time, there was no concept that was telling that a photon or a wave can actually kick another particle. It can collide with another particle. That concept was not there. But Compton effect showed that photons can actually collide with electrons and behave as balls, you can say, billiards balls, you can say. Now, if you have played pool or carom, you can see one of those coins in a carom board would collide with another coin and it would produce deflection, isn't it? So it would produce collision. Same thing was happening here. Similarly, the de Broglie's wave hypothesis also confirmed that electrons, which were supposedly particles as explained by Bohr, Thomson, and in a little bit by Rutherford as well, Bohr's hypothesis proved or showed that these electrons are actually waves. They are wave like. There were a number of more such experiments which collectively confirmed that classical physics was not sufficient in trying to explain the behavior of these small particles. And this is where modern physics comes in the picture. This is where we understand what is meant by your quantum mechanics. Quantum mechanics talks about these types of particles itself. It talks about particles that can behave as particles and as waves. Their behavior, their interaction with nature, their interaction with external, what's it called, environment, external forms of energies. And coming to this, there was a question: if I cannot study all these particles with the normal physics, what should I do? There was one very interesting answer to this. We come to realize that energy is perhaps the most dominant concept in physics. What is energy? In terms of a mathematician, all right, a simple mathematician, which all of you will have to become for some time to understand quantum mechanics in its pure essence. Energy is a function. A function of what? It's a function of various properties of the particle. And this is very important for you to understand. Energy is not an a beam of light as you have seen in Dragon Ball and all. It's just a function of the properties of the particle. What properties? Its position, its velocity, its momentum, its temperature. Any property that you can think of about the particle, a function of that property is nothing but energy. So, what happens? The behavior of a particle or even the behavior of a system can be explained by looking at its energy. By looking at its energy. Now, let's see a simple example for this, okay? Let's say I have a multi-storied building. So let's say this is the first floor, two, three, four, five floors. So there is a, you can say, a man with a small ball in his hand that can be thrown from the window through any one of these floors. Let's say the height of each floor is h naught. It's a constant. The height is a constant here. So, what are the possible values of mechanical energy associated with this ball, which is initially at rest? It can be here, it can be here, or here, or here, or here. Right? Now, you can see the energy of this ball can be expressed as 0 times mgh naught if it is present on the ground floor. It can be 1 time mgh naught or 2 times mgh naught all the way till 5 times mgh naught. Now, of course, there is a certain height here itself, but this height is much smaller compared to the entire size of the floor. So, right now we can neglect it. Or if we don't want to neglect it, you can just write it as some delta E. A small interpretation you can see is some value of delta E. Now, as such, you can see if I take mgh naught as E naught, it's a constant value, right? M is the mass, G is the acceleration due to gravity, which does not change a lot from the ground floor to the fifth floor, right? So we have fifth, actually it would be 4 mgh naught when the body is at this position here. So coming back, you would see that the energy of the ball can be written as n times E naught, where n can be 0, 1, 2, 3, and 4. Now, what you have created right now here is what we call a quantum model of a system. A quantum model in which the energy of the particle or of the system can be expressed as a quantized version or quantized multiple of a unit value. Quantized means what? Quantized means that the value or the quantity is available in discrete packets. Discrete packets. So what you have here, if we talk about the particle present at the ground floor, its mechanical energy is n times E naught, which is equal to 0 times E naught, which is 0. If the particle is present in the first floor, it becomes 1 times E naught. Second floor, 2 times, and as such, so on and so forth. Now, how would we understand the behavior of the particle? If we can simply construct a device that can calculate the final velocity with which the particle was thrown, and that type of a device can simply be a spring which is kept on the ground. Then, if the ball is thrown here, thrown on the spring, then the compression of the spring can describe the energy of the ball, which in turn can describe where the particle was initially. It can describe where the ball was initially kept. If, let's say, the spring compresses by a distance, let's say delta x, which corresponds to mgh naught, this would imply that the ball was present in the second floor. If the spring compresses by 2 times delta x, then the ball was present on the third floor because the energy would become 2 times mgh naught. Now, this is a very simple model which tries to explain how we can use energy to understand the initial configuration of a system. Of course, this was not that interesting because it was a very what's it called simple experiment. But instead of the experiment, if we focus on what this was trying to tell us, was that using the energy of interaction of a particle, we can come to understand the original configuration of the particle. This is very important, and this is one very big difference between classical mechanics and quantum mechanics, or classical physics and quantum physics. In classical physics, we can actually come to a result without performing the experiment. We can come to a conclusion about the system without even studying about the experiment. But here, we can only talk about the system once the experiment is conducted. Unless you threw the ball on the ground, unless the spring got compressed, is there any way in which you can talk about the energy of the ball using this experiment? No. So, this is one very important concept. Experiments need to be performed in order to come to the result. So, in this approach, quantum mechanics was a very experimental science. So, you can see here, we can do the same thing, the exact same thing with an atom. You take an atom and you have the electron, the last shell electron of the atom, and you give it some original energy, some initial energy from outside. You can do this by heating it, or you can do this by putting the atom in an external electric field because the electrons are charged, they will gain some energy. You can keep it in a magnetic field because the electrons have some magnetic properties as well. They will also interact with this magnetic energy and they will start to experience some forces or some energies. And using these energies, they will produce a result which can be seen either through naked eye or by using a spectrometer, a telescope. And this entire experiment is called spectrometry. Spectrometry. You will see that this is the only way in which we can study small particles right now, as of now. We only try to take that particle or the system, we try to make that particle or system interact with an external energy and then produce a result. Just like the ball in the building was interacting with the spring and producing a result. In the same way, the electrons of the system and in general, every quantum mechanical system interacts with a form of energy and then produces a result, which is the outcome. Now, the interesting part is that this experiment can be expressed mathematically as well. And that is what makes quantum mechanics something very advanced. In quantum mechanics, we don't actually have to perform these experiments. And this is important. Normally, you would say that, okay, I'll actually have to take the atom or the electron, I have to, throw it in a system having some electric or magnetic field, and then I'll have to actually use a spectrometer to see all this. That is tedious. But the interesting part is that you don't actually have to do all this. You have a very simple mathematical method of performing these experiments. Now imagine taking this entire experiment and performing it without using any tool, just by using mathematics. I'm going to demonstrate one simple method here. What I'm going to do is I'm going to perform this experiment using mathematics. To perform this experiment, we need certain entities. The first entity is called an operator. The second entity is an identity of the system, and the result of the experiment would look as such. Now, I know right now this looks very complicated, all right, but I'll explain this to you. This symbol here, the Greek symbol, which is called psi, is actually representing the system or the particle. It's a representation, a mathematical representation of the particle. All of us have our ID cards, like our Aadhaar cards or PAN cards and whatever. So this entity here, which is called a wave function, represents the particle or the system mathematically. The act of performing the experiment is seen here. This here is called the instrument, or what we call in physics or mathematics, operators. And the result of the experiment is this, which we call eigen value, also called observable. This is how quantum mechanics becomes a theoretical science. What has happened here? Here we have taken the experiment and using a lot of complicated mathematics, and we have simplified it actually. We as such do not have to study how these operators came into existence. Of course, we can study if we wanted to. But our job is to understand how these experiments can be conducted mathematically. And this itself is quantum mechanics. Now, to understand this, as I've explained already here, energy of systems is a very important part in understanding quantum mechanics or in understanding the behavior of these quantum systems. Now, you would see that the energy of the system, the entire energy, which is called Hamiltonian. This is just another fancy word that we have for the total energy. Hamiltonian is nothing but the sum of the kinetic energy of the system, which we represent as capital T, and the potential energy of the system, which we represent as capital V. Now we change the names just to make it easier for us to write, and this is the common notation that is used everywhere. So Hamiltonian is represented using an H. So I could say that H is equal to T plus V. Now this is a simple result of classical mechanics, but this itself will give us the entire topic of quantum mechanics. So how? The second part of this experiment or this topic is Schrodinger's equations. Now, so Schrodinger tried to do the same thing. He tried to figure out the energy of the particle, all right, energy of particles and energy of systems. And he tried to create a simple equation that can help us understand the entire mechanism of such particles. For that, what he did was a simple result. He took the total energy, which was equal to T plus V, and he tried to modify this equation using some simple results. The first was Planck's theorem. Planck's theorem proposed that the energy of a smallest particle, which is a photon in this case, energy E, was equal to h, which is a Planck's constant, multiplied with the frequency of the material. H here turns out to be 6.62618 into 10 to the power minus 34 joule second. All right. And nu, this is not V, this is nu, is the frequency of the wave. So you can keep, instead of the energy or the Hamiltonian h, you can keep small h into nu. This would become equal to the kinetic energy. The second theorem that he used was de Broglie's wave hypothesis or wavelength equation. Lambda was equal to h by p, which turns out that p is equal to h by lambda, or h by 2 pi times 2 pi by lambda, which now becomes equal to h cross times k. This element here is written popularly as h cross. Just saves time, that's all right. So kinetic energy, which is equal to momentum square divided by 2, and this is a simple equation, all of you know this, half mv square formula, turns out to be h cross square k square by 2m. plus V, the potential energy. Now we cannot give an exact result to potential energy. The reason for that is because potential energy depends on the type of interaction. Type of interaction. If there is no interaction, then potential energy just becomes zero. It just becomes zero. So we will leave potential energy as it is. We will only know that potential energy is a function of the position of the system. So where this particle is, where this photon is present, or where this electron is present, that position will determine the potential energy of this. The third help that Schrodinger used was from Maxwell's equations. Now, Maxwell's equations are wave equations of electromagnetic energy. And you all know, and we all knew by that time, that a photon is a quantum packet of electromagnetic energy. So, Maxwell's equation gave a very clear understanding of how we can use the results above and turn this into a wave equation. So, what was Maxwell's equation? According to Maxwell's equation, an electromagnetic wave, an electromagnetic wave, which is symbolized as psi, that same Greek alphabet psi, can be represented as an amplitude multiplied with e to the power of iota k dot r minus omega t. Now, A is the amplitude, E, all of you know, is the Euler identity, K is the same K that we have used here. This K here is the same thing. It is called wave number. All right, it's a part of the wave equation of a wave. R is the position, omega is the angular frequency. Omega is the angular frequency, which is equal to 2 pi times the frequency of a material, of a wave, that is, and t is time. Using this equation, we are able to convert this in just 2 to 3 simple steps. It's not something complicated. And the equation becomes I h cross times dou psi by dou. This is differentiation, partial differentiation, meaning differentiating the wave function with respect to time, becomes equal to minus h cross square by 2m times the double derivative of the wave function with respect to position now, plus v of x times psi. And the method to do that is very simple. What you do is you extract the value of k, you extract the value of k by differentiating psi with respect to position, and you extract the value of omega by differentiating psi with respect to time, because the coefficient of omega is time and the coefficient of k is position. And you just put these values in this equation and you come to this result. Now, what is the Schrodinger's equation? Schrodinger's equation, which I'll just write once again, IH cross dou psi by dou t is equal to minus h cross square upon 2m times dou 2 psi by dou x square, this is psi here, plus Vx of psi. This Vx is nothing but the potential energy. Psi is nothing but the wave function. I h cross, I is iota, h cross is again h by 2 pi. All right, and m is the mass of the particle. Now look at this wave equation. This is something very interesting. This is a very new form of equation that was introduced in physics, which showed two different results. First, it has kinetic energy and it has potential energy. It also carries mass. Isn't it so? Technically, this shows that the equation is representing a particle. On the other hand, we have wave functions, isn't it so? This quantity itself, if you remember, was having k, the wave number. Now, what is this wave number? Simply put, wave number is 2 pi divided by wavelength. All right, it is 2 pi divided by the wavelength of the material, wavelength of the wave, the mechanical wave or the electromagnetic wave or whatever it is. So, as such, it is also representing a wave. So, what are we seeing here? We are seeing that this Schrodinger's equation represents both a particle and a wave. As such, this was the perfect equation that can be used to study such particles. Particles that are behaving both as matter carrying some mass and waves carrying some wavelength. All right. So what happens here is that this equation, even though this equation is a very simple equation, it looks complicated, but trust me, it's not complicated at all. It only looks complicated. Even the name of the scientist is complicated, Schrodinger, isn't it so? So what happens here? You can simplify it a little bit by removing or eliminating time. If you remember, this was nothing but the total energy of the particle or the Hamiltonian of the particle, if you remember, multiplied with the wave function, which is also multiplied here, also multiplied here. This here was the kinetic energy multiplied with the same wave function, and this, as you can see, is the potential energy multiplied with again the same wave function. How do I know it's multiplied everywhere? How do I know that the wave function is multiplied? Because it's multiplied in the potential as well. So what do we have here? We have the energy of the particle multiplied with the wave function equal to minus h cross square by 2n times dou 2 psi by dou x square plus vx times psi. This, as you can see, depends on time and position both. So this is called the time dependent Schrodinger's equation. And this here is independent of time, hence the name time independent Schrodinger's equation. All right. So what we have seen so far, we have seen that quantum particles are very different from your normal mechanical particles. How are they different? They're different because they can behave both as waves and as matter. The second thing we have seen that the inability of classical physics to try to explain this, because normally classical physics studies waves separately and particles separately. It does not study both of them together. All right. Third thing we have seen that using some interesting experiments, some interesting approaches and results that were given to us by different physicists and mathematicians of that time, Schrodinger was able to create a set of equations, two equations specifically, which would collectively describe the behavior. Now, how does it describe the behavior? Right now, we have not seen that. We'll see that in a moment. But collectively, it is aimed at describing the behavior of such particles. We don't have any other tool. We have also seen how energy is so significant, so important here. If we don't understand energy or if we don't understand interaction between systems using energy, we cannot understand how these particles behave. So this is very important. Okay, now moving forward, you will see that when we talk about these time independent or time dependent Schrodinger's equation, as such, looking at them does not make much sense. There are certain flaws as well in these equations. Now, what are the flaws? The first flaw is the most important flaw is that these equations are complex in nature. Isn't it so? Obviously, the second equation has been derived from the first equation as well. So it will not be right to say that it is not a complex. Complex meaning having real plus imaginary numbers. For those of you who do not know what is iota here, the iota is the root of -1. It is a number that you can never find on the real number line, no matter how much you try. That's why the name imaginary number. You cannot try and ever find the value of iota here. So that's the reason we call it an imaginary number. So coming back. So how do we understand more about this wave function? Uh, Jeevan, are you there?
Yes, sir.
There are some annotations on the screen.
Not really.
Can you see them?
No, I don't see.
A red line, you know?
No, I don't see. You see it, Sitara?
Yeah, now I can see it. Yeah, I think I can. Yeah, I think it's gone now, right?
Okay, no issues as long as you all can see it.
Yeah.
Okay,
I don't-
moving on to the next part. Now, what is the use of Schrodinger's equation?
Alan, we can take a couple of questions if they want to now, maybe, or you can
Um, we'll just finish a few more
finish
topics.
this.
Yeah,
Yeah.
a few
Okay.
more topics, and then we'll stick to the schedule. Okay. Students, if you have any questions or doubts, please write them down and note them. Right after a few more topics, we'll have a brief discussion session. So, the use of Schrodinger's equation. As you have seen before, Schrodinger's equation aims at trying to understand the system using its energy. How to do that, even Schrodinger did not have any idea. The simplest thing that we can think of right now is to be able to solve the Schrodinger's equation. Solve the Schrodinger's equation. Now you can see the Schrodinger's equation is not an ordinary type of an equation. Such an equation is called a differential equation. And when you solve the differential equation, specifically when you solve the Schrodinger's equation, the solution of Schrodinger's equation is going to be nothing but psi itself. This here is called a wave function. Now, same question again. What is this wave function? Now, a very simple understanding of the wave function is that it is a bag of information about the particle or the system. Now, this is very important for you to understand. Individually, psi makes no sense. If you just look at the wave function, it is meaningless. It does not make any sense. Obviously, it has a mathematical value, but it does not make sense in physics. So, why do we use it? Because you can extract any information you want about the particle from this equation. And this is actually true. For example, the wave equation of an electron present inside the shell. Let's talk about the first shell of the hydrogen atom. Psi is something like a constant A, which is 2 by A naught to the power 3 by 2. We don't have to worry about that. Times e to the power minus r by A naught, where A naught is Bohr's radius, which is equal to 0.529 angstrom. Now you can see this. It does not make a lot of sense, isn't it? So you can see that this component here is dimensionless. A, on the other hand, will have the component of length, the dimensions of length, and it's not going to be to the power 1, it's going to be to the power of 3 by 2. All right, so it's going to be L to the power of minus 3 by 2. So in itself, it does not make sense. but you can extract any information that you want from the Schrodinger's equation or from the wave function, any single information. And how do we do that? We'll see that in some time. There are certain mathematical functionals here that we are going to be using now. These functionals are called operators. These functionals are called operators. Now, what is meant by operators? They are functionals. Now, for those of you who know functionals well and good, for those of you who don't know what is meant by functionals, it is a very simple concept. For example, you have a variable x and then you have a variable y, right? When you multiply these two together, this is an operation that you are performing on these two variables, isn't it so? This is called an operation, or simply, this is called a function, right? You can write this as a function of x and y. We normally write this as a function of x comma y. So what do you get? You get x into y, right? So whenever I give you two variables, so let's say u and v, let's say u is equal to 2, v is equal to 6. So the same function of u comma v would become equal to what? 2 into 6, which is 12. So you will get a result. Similar to this, if I give you two functions itself, for example, a function f1, which is equal to 2x square y, all right, some let's say function, and I want you to perform an operation on this function itself. For example, I want you to divide the function with x, or let's say I want you to differentiate it with respect to x, or let's say with respect to x square, or let's say I want you to integrate it with y. These are operations performed on a function. These operations are called functionals. In physics, we call these operators. There's a special class of functionals that is used here, which are called linear functionals. Now, normally in physics, we only use linear functionals in quantum mechanics as far as these operators are concerned. Now, how are these operators used? Take a look here. You remember I told you that the wave function is nothing but a collection of information. I expect, actually I told it's a bag of information, bag full of information, a collection of information. So how do you take out these informations about the particle? How do you extract the information? You do that by using specific operators. For example, if let's say I want to find out the momentum of a particle represented by this wave function. All right. As an example, I'm going to use a typical type of an operator, typical type of a wave function, a e power I k x. A e power I k x. This is a wave equation or a wave function of a free particle, which we'll see a little later. So this is an example. Now I want to find out the momentum. What is the momentum of the particle? As such, the wave function makes no sense. But if I want to calculate its momentum, there is an already created list of operators for different types of quantities. For example, if I want to find momentum P, the method for that is to multiply IH cross with a minus sign and then differentiate the wave function with respect to x. All right, what do we do? Minus IH cross we multiply after differentiating the wave function with respect to x. So the result of that, whatever result we get from there, would be the momentum. And we'll see if this is actually true or not. We would see that P acting on the wave function. Now, normally the momentum or any other operator is represented by a small cap at the top of its head here. So you will see P cap acting on psi would become minus IH cross dou by dou x acting on this wave function. a e power I k x. Now, when you differentiate it, almost all of you are familiar with differentiation, so you would know this. While differentiating, ik would come out, so this would become minus ih cross times ik times a e power I k x. This will be the result of the differentiation and the entire interaction on the other hand. Multiply these two together, what would you get? You would get I times I, iota times iota becomes minus 1, because I just told you I is equal to root of minus 1. So minus 1 into an already minus sign here will become plus 1, and you will get h cross k times a e power I k x. Now rewriting this just once again, you would see p cap acting on psi finally gave us h cross k acting on the same wave function a e power ikx, a e power ikx. So I can simply cancel these two, and what am I getting as a result? I'm getting h cross k as a result. Now is this momentum? Let's see a little up. Take a look. Momentum was in fact h cross k. Got it? So what did I do here? I actually performed an experiment in which I calculated the momentum of the particle without performing any experiment in reality. All of this is mathematics. It's completely mathematics. And without performing any actual experiment, I can get results about the particle. There are a number of such operators. You have the position operator, x cap, for which what you have to do is you just have to multiply x cap, just an x, for example, if it is a y, you multiply a y with the wave function, and the result of this would be the position of the particle or the system multiplied with the wave function. When you want to find the momentum, as I've already shown, you have to do a little more complicated thing here. You have to multiply minus I h cross and then differentiate the wave function with respect to position, and you will get the momentum of the particle multiplied with its wave function. Of course, these can be cancelled out later. These can be cancelled out later. Then you can calculate the kinetic energy of the particle. T, you remember T was nothing but kinetic energy, which was equal to minus h cross square upon 2m, minus h cross square upon 2m times the double derivative of the wave function, and this would give you the kinetic energy multiplied with the wave function. And we have actually seen this already. You will see in the development of the Schrodinger's equation. See here, wasn't this the kinetic energy multiplied with psi? Remember, I had told you that this is nothing but the kinetic energy multiplied with wave function, potential energy multiplied with wave function, and this here is the mechanical energy multiplied with the wave function. See here, kinetic energy multiplied with the wave function, minus h cross square by 2m times the double derivative of the wave function. So you come to understand that all these are now becoming a little simpler. There is, of course, a little advanced version of mathematics involved here, but it's not something very complicated. You can also see that the total energy H cap was found by using IH cross dou by dou t. IH cross dou by dou t, which is also seen in the beginning here, as you will see here. IH cross dou by dou t of psi, which was nothing but the total energy multiplied with the psi. Right? So the result of this would be the energy multiplied with psi. Next one, and of course there are more, and it's not something that where very complicated that you have to memorize, you can create wave functions by yourself as well. You can create operators by yourself as well. For example, you all know that angular momentum is nothing but position multiplied with momentum. So you take the position operator, for example, x, multiply it with, let's say, py. This would become equal to what? Lz, the angular momentum along the z-axis. Got it? This is simple cross product of vectors that you all know already or should know. Similarly, you can find out any other type of an operator using this. The total Hamiltonian operator is also found by using, which is this one here, is also found by using the kinetic energy operator, adding it with the potential energy operator. Potential energy operator, on the other hand, is simply the potential energy multiplied with the wave function. We come to the final conclusion here that an operator, any operator, let d cap be an operator, when multiplied with a wave function, should give a result of that experiment multiplied with the same wave function. Now, this thing here is the act of performing the experiment. This here is the result of the experiment, and this here is nothing but the particle on which the experiment is conducted. In physics, the act of performing the experiment is called the action of an operator. The result of the experiment is called the observable or the measurable, and the particle itself is represented as a wave function. Whereas in mathematics, this here is a linear functional. This here is an eigenfunction. The wave function in mathematics is called eigenfunction, and the result is called eigenvalue. So I think we should be open to questions if there is any. Siddharth?
Yeah, we can take some questions now, guys. So whoever wants to ask anything about whatever he taught now, or if you even have any more general questions related to quantum mechanics, now would be a good time to ask. So we'll just take a 5 to 10 minute break. Yeah.
Hello, Alanza. I have a question.
Yeah, then.
So, how are these operators like for extracting the momentum info from the psi, that's the wave function? How do you know that it is like minus IH into dou by dou x of that? So how is it derived?
They're talking about the derivation of these wave functions. Now,
yeah.
It's not something very complicated. We can derive them as well. But typically, the position operator and the momentum operator, if you take these two as postulates, then every other operator can be derived using these two. Now, derivation of these as well. For example, momentum of position operator is fairly easy. Momentum operator is also not that difficult, and this requires a little bit of just some mathematical manipulations here. For example, I use the equation a e power I k x, right? Now, when you differentiate this with respect to position, what do you get? You get I k times a e power I k x. Now you already knew that the result of the momentum during the derivation, as you can see here, was h cross times k. So what would you do here to modify this? I has to be removed, so you multiply a minus I here and put an h cross. Got it? Now there are, of course, more general methods of derivation. All right, you can see ik here is equal to negative gradient. So differentiating this with respect to position, that itself means this. And an h cross comes in order to, what's it called? Uh, Take care of the dimensions. So if you take these two position and momentum, you can derive anything else. For example, if you take talk about kinetic energy. So what is kinetic energy equal to? You know the formula momentum square by 2m.
Yes, sir.
So momentum square would be equal to what? Minus I h cross dou by dou x the whole square divided by 2m, right?
All right, got it, sir.
Squaring this would give you minus I square is negative minus 1, and h cross becomes h cross square. Double derivative of this, dou 2 by dou x square, and then dividing by 2m, and you get minus h cross square by 2m double derivative. Understood?
Yes, sir. Thank you.
Okay.
Excuse me, sir.
Yeah.
Sir, is Bayes' theorem and EPR paradox in our syllabus, in BSc syllabus?
It's not a part of your syllabus per se, but it's not something that is outside your syllabus also. You can study it, but for that you have to cover some more other topics as well. For example, if you want to study EPR paradox, you have to first understand how information is propagated through space-time. All right, so there is a lot of classical mechanics involved there, a lot of quantum mechanics involved there, quantum entanglement is involved there. All right, so all that is there. So only after you cover those topics, then you can come to these topics.
And sir,
Um,
what these operators that you mentioned, are all these operators given in any beginner's quantum mechanics book?
I didn't understand it. Just repeat again, please.
Yes.
sir,
One second. Just repeat the question. You were asking these operators are given what?
Are the operators in like any standard beginner's
Any, yes,
quantum?
any and every book will give you the list of operators, and you can create them. Like I showed before, also, you don't actually have to sit and memorize these two, position and momentum. If you know, you can derive all the others by yourself. So it takes maximum half an hour to write down a list of all the operators.
Okay, sir. Thank you.
Okay. Yes. The next question, please.
Sir, I had a question.
Huh.
When we say the energy is Planck's constant and frequency
Huh.
multiplication, so obviously we are thinking of the energy of the wave. So do
Yes.
you mean to say that when we quantize
Hmm.
each discrete part of that wave, so that packet of the energy we can think of as particles?
Yes. We do not think of them as particles. These packets of energy behave as particles. All right. For example, you're talking about a photon. You're referring to a photon. All right. There, and you must be knowing this already, that there are many evidences to show that even a photon, which is in reality a wave packet, also behaves as a particle. Right?
Yeah. Why I'm asking that is I want to take to the next level.
Okay.
Because whether anything which has a wave has to
Hmm.
have some mass, or we can any zero mass can produce a wave. So that's the catch, because what I thought is if
Hmm.
each quantized part is a particle, then we can intuitively understand the relation between duality principle. But then
Okay.
whether you have to have some mass to produce a wave, or a zero mass can produce a wave, that's the question.
Okay. Okay. See, there is a much simpler answer to your question. You're saying that, in simple terms, you're saying that every material particle can behave as a wave, and every wave particle can, or every wave packet can behave as a particle.
At a
So there is a
microscope level, at a microscope level.
microscopic level, definitely microscopic level. So there is a simpler reason for that. There is a simpler explanation for that. Okay, if you have any two wave packets, all right, that can be confined in a system, then that packet will behave as a particle. If you have any wave packet that can collide or interact with the momentum of any particle, then that wave packet will also behave as a particle. Okay? If you have any particle that is showing an uncertainty in its position, which is bigger than its own size, it will behave as a wave. Understood?
Yeah, to some extent. But that means the corollary is we can't think of any zero mass thing producing wave. Is that correct?
No. We can always think of zero mass producing wave, but having zero mass is not actually a topic of quantum mechanics. Having zero mass just tells you that the particle will start moving at a very high speed, the speed of light.
Okay. Thank you.
Okay.
Thank you.
Hello, Lancer.
Sir,
Yes.
sir, I have a doubt, sir.
Please ask.
Sir, how many atoms is gravity made of?
Gravity is not an object that is made of atoms. Matter is made of
Okay,
atoms. Gravity is an interaction. All right. For example, if I'm talking to you right now, there is a transfer of energy, right?
yes, sir.
This transfer of energy in physics is called interaction. Got it?
Okay,
So gravity
got it,
is
sir.
a transfer of energy, which is basically gravitational potential energy and some kinetic energy. Got it? So that is an interaction. Now, if you refer to some very new concepts in physics, gravitation is caused by, it's not composed of, it is caused by small particles which are called gravitons. All right, so they are the effect carriers. So, for example, everything gets attracted because of gravity, right?
Yes, sir.
Why is that so? The reason is that these small particles called gravitons, all right, which again are quantum particles because they're very small, all right, they exert this interaction from one particle to the other. They take this interaction energy from one particle and take it to the other particle, and that's how these two particles interact. Okay,
Okay.
so it's
So,
not
sir,
matter. Yeah,
if 1,000 atoms is equal to thin sheet of paper, how much do you think Earth will be equal to how many atoms?
it's a very simple calculation, but you can just think the total mass of the atom is somewhere close to 10 power minus 27 kg. The mass of the Earth, on the other hand, is somewhere close to 10 to the power 24 kg. All right. So a simple division of that 10 power 24 plus 27 would give you the result.
Okay, sir.
Yeah.
Thank you.
Hello, Lancer.
Yes, please tell.
Sir, hello, sir. It is
Hello.
sir. I read in a book that the measurement collapses the wave function.
Measurement
Measurement
collapses the wave
wave
function. Yes,
function.
correct.
If we measure momentum and the position through this operator,
Mhm.
do we think that what we are measuring is right or wrong, or how can we know that whether we are the measurement is right or wrong? Because the statement says that if we the measurement collapses the wave function.
Correct. Okay. Now there are two very important points that we need to understand here. First, the statement that the measurement or the act of measurement collapses the wave function means with respect to, or is the statement is given with respect to the statistical interpretation of quantum mechanics, which was the next topic anyhow. What happens here, the statement means something very different from what you're understanding it as. The act of measurement collapses a wave function. It does not collapse the wave function, it just collapses the statistical distribution of the wave function. For example, let's say in a box there are four chambers, all right, and I throw a particle in that box. Okay, now what is the probability of finding that particle in any one of those chambers? It's simply 1 by 4.
Sir,
Agreed?
okay, I can
Okay.
understand. I got it.
Okay. Now, if you actually perform the experiment, what is the experiment? You open the box and then you see it and you see the particle. Then what will happen? the probability of the particle being found in four chambers or three out of those chambers will become zero, and only one chamber will become one.
Yes, sir.
So what has happened? The wave function, which was initially giving you a result of probabilities in all these four boxes, has been collapsed and is now giving the result only in one box. There is a simple way to what's it called? Understand this. I can write the wave function of such an experiment as 1 by root 4 times segment A or this chamber A plus 1 by root 4 of this chamber B plus 1 by root 4 of this chamber C and 1 by root 4 of this chamber D. So these are nothing but the square roots of probabilities. All right. So the probability of finding the particle in each chamber was 1 by 4. So the square root of that becomes 1 by root 4. This is called probability amplitude. All right. You remember for wave functions, I was giving that there is one amplitude and then there is one exponential function. This amplitude is this one here. Now, when you perform the experiment, the act of performing the experiment, what happens? Suppose the particle is actually in the what's it, compartment D. Will this wave function still be correct?
May be wrong.
It
May be
definitely will be wrong, because when you throw the particle and you open the box and you actually see the particle, it is not possible that you will find the particle in all these four boxes, right? They can find it only in one of the chambers.
yes, sir. Right.
So obviously, three of these will get cancelled and only one will remain.
Ah, okay, sir. I
That is
got it.
what is meant by collapsing of the wave function. Okay.
Ah, okay, sir. Sir, in continued, the last one who asked that, you said that the wave is the packets of energy. Is that mean the wave is made up of small particles?
The wave is not made of small particles. See, what happens here is that whenever we talk about a wave, okay, wave is nothing but a bundle of energy, right? Now,
Yes.
it can be a continuous flow of energy or it can be a quantized flow of energy. Okay, let's understand what I mean by that. You take a string, for example, the string of a guitar. Okay, now there is a way in which you can pluck it. Right now, it's at rest, right? So there is a way in which you can pluck it continuously using a violin bow or something, in which it will continuously keep vibrating. Isn't it so?
Yes, sir.
So this is a continuous energy flow. The particle or the string in this case is getting the vibrational energy continuously, constantly with time. Right? Then what would happen? You take the same string and you pluck it now, and then you pluck it once again, once again, once again, once again. What is happening? Now the energy is supplied in discrete packets, right? Hello,
Yes,
hello.
sir. Yes, sir. I am listening. You can
Ah,
continue. Yes.
so the energy is now provided in discrete packets. Now these discrete packets is what is meant by the quantized nature of wave. Okay, so the wave is now being provided in packets. Each packet of the wave, each individual packet of the wave can have particle like nature. It's not actually right to call it a particle. We should call it particle like. Got
Okay,
it?
sir.
Does this answer your question?
No, sir. Thank you so much.
Okay.
I just, if I can add on, coming back to that wave function collapse. So
Yes.
what does it actually mean is, when we measure, we see a particle. If we don't measure, we don't see the particle.
Yes.
So
So the accurate result of an experiment cannot be given unless the experiment has been actually performed.
yeah. But that's okay. Till that, up to that point, is okay. But
Hmm.
that means, but in the physical reality, there is no particle. It's all wave. Unless you see it. Suppose I don't go and measure. So
Okay.
then, what is actually the physical reality at a very fundamental scale? It's only wave. There is no particle.
No, 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 that's not true. If you are not making an observation, how can you be sure that there is a particle and not a wave, or there is a wave and not a particle?
But that's exactly the collapse of the collapse of the wave function in indirectly telling you can see it as a particle only when you measure it.
Okay, okay, I understood
You
what you are
understand now?
referring to.
So my point is, I don't want to measure it, but I just want to understand the physical reality at the very fundamental scale. So that
Okay.
says that it is all in wave form. Till I measure, I won't see it as particle. Is that correct?
No, no, I'll explain what I've understood what you're trying to explain. Now, you are referring to the wave function as the wave nature of a particle. Am I correct?
Yeah.
This is a mistake actually. Wave function does not represent the wave nature. Wave function just represents the properties of the particle, regardless of the fact whether it is a wave or a particle. So when the statement says wave function collapse, it does not say that the wave nature collapses. So I'll
Actually,
explain this to you with the help of an example. Okay.
what animation we saw it, as you say
Hmm.
correctly, the psi describes the entire wave. So
Yeah.
the entire wave, we brought it collapse to a spike completely without any wavelength, zero wavelength spike.
Okay.
So
So
that,
that is a very particular type of a wave function that you're talking about.
okay, okay,
That is a very particular type of a wave function that is called Dirac's distribution. All right, there are two types of, actually, there are three types of waves that you're going to see in quantum mechanics. First is the plane wave. The second is what's it called, Gaussian distribution or Gaussian wave packet. And the third one is a Dirac distribution, which, like you suggested, is a small spike. A
yeah,
spike at x equals to a certain x naught. Everywhere else it is zero. That's what you're suggesting, right? But take a look at a very simple, what's it called, result from this. You are suggesting that there is only a single particle at a certain location. So the error in its position is zero. Agreed?
yeah, yeah, yes, yes,
If the error in the position is zero, then according to the uncertainty principle, the error in its momentum will become infinity.
mhm,
So again, we will not be able to measure the particle nature of this supposed particle. So when we talked about this chamber problem, for example, it is true that once I actually perform the experiment, I can say that the particle is present in one of the chambers. For example, this is the fourth chamber. It does not mean, however, that I'm still certain, because even the chamber has a certain length, right? It has a certain size. And whatever be the size of the chamber, the wavelength of that particle will still be confined in this chamber. All right. So
okay,
the simplest understanding of this is the wave function has nothing to do with the wave nature. All right. It only tells about the information about the entity. Whether it is a particle or a wave does not matter. Using the same wave function, you can calculate the momentum of the particle also, suggesting it is a particle. And you can also calculate the wavelength, suggesting it is a wave, right?
yeah,
So it is not saying whether it is a particle or a wave, right?
okay, okay,
We just call it a wave function. It is not trying to say that it is a wave. Just the name is wave function. That's it.
okay. Thank you. Thank
So before we move ahead, I've just put up a quick announcement on the group. So we are planning a more elaborate workshop. Like clearly, we have a time constraint, and before we know it, it's actually already been 2 hours since we started. Almost. So, we just want to say that there's like so much to learn. And I think getting a little bit more familiarity with this particular subject could be very interesting for all of us, whether or not you're planning to write an exam in the near future. So, the 27th, 28th, and 29th of this month, which is a Friday, Saturday, Sunday, we are going to be arranging a 3-day rigorous workshop on quantum mechanics. So this is, again, it's going to be from the scratch, so you don't have to worry if you feel like you don't have much of the basics or whatever. Like you see, he's going to be starting from the beginning, and he's going to be trying to cover most of the topics. So Alan, can you tell us a little bit more about what other topics you'll be trying to cover in the weekend workshop?
Yeah, so in the 3-day workshop, my plan is to cover the entire syllabus of quantum mechanics to the degree level. All right, so the course will be both focusing on the content that is your the syllabus that is supposed to be covered for quantum mechanics, and also an introduction to some research opportunities that in quantum mechanics. I remember some of the students had asked when we had conducted one seminar before that there were some possible asking if there were some possible research options in quantum mechanics. So I'll be introducing some of that as well. And along with that, it will also be from the exam point of view. So if any one of you are preparing for any exams and anything, this would be like the first course that you are going to cover, the first time lesson that you're going to have for quantum mechanics. So we are going to cover everything from the mathematical aspects, everything in detail along with the derivations and everything. So it will be a 6 hour program collectively for 3 days, divided into 2 hours each. And you will have some assignments as well. You'll have some, what's it called, projects as well. And some questions, some very interesting and important questions, the type of numerical problems that comes through, comes from quantum mechanics, all that will be covered as well.
Yeah, I think it's going to be great fun because quantum mechanics is something that we are yet to, we're just starting to explore. So if you're either slightly new in the subject or if you studied it a while ago and you want like a good refreshers course, then I think either way, this is a great opportunity for you. And one more thing is it's kind of priced slightly, higher for other people, but the participants who are here today, like the 20, maybe 22, 23 of you right now, we are going to give it to you at like a cheaper rate. So we just want to say use this, and since it's starting in just around a week, um, I think it's a great way to learn in a very quick amount of time. We're not extending it for like 20 days, 30 days. We want to give you a very quick, condensed and intensive workshop. So I'm putting out another link as well. You can use either of it. Don't try to fill both. And there's not much information. It's a direct, it just asks you for your name, your email ID, and you can directly pay right now. So you can use either of the link, whichever suits you. If you want to use Google Pay to pay, then you have to use the forms. Otherwise, you can use the InstaMojo link. So if you have any other questions about what topics are going to be covered in the workshop, you can you can ask him right now. Is there anybody who wants to address the workshop or talk about what else is going to be covered there?
Yeah, but like we can do that at the end maybe, because like not everybody here may want to attend that workshop, right?
Yeah. So let's do that. So since because of the time constraint, I just want to say, Alan, can you finish the rest of the portions in maybe around 15 minutes?
15 minutes
to
will not be, we'll wrap it up within 20 to 25 minutes, definitely.
Yeah. Okay. Yeah. Let's do that.
Okay. All right. So should we continue? Should we start?
Yeah. You can continue. Yeah.
Okay. All right. So in the first part of this lecture, we had seen how Schrodinger's equations help us to understand the what's it called uh, quantities or any set of information that is associated with the particle. And of course, to do that, we need the operators, the certain set of operators which can be derived as well. One very important and interesting question was there to figure out how to be certain that our results are accurate, because as you saw, one of the questions was that if the particle is present in one of those four boxes, so how do we know for sure that the particle is present in one of those boxes? To do that, Max Born had given an alternate interpretation of Schrodinger's equation, which was called the statistical interpretation of Schrodinger's equation, in which, using some simple mathematics, he proposes something very interesting. The first proposal was psi, the wave function, represents the statistical distribution of the particle in the space. What does this mean? Take a look here. If let's say psi is equal to a e power I k x. Let's say, as an example, this is the most common example that we can use. There is a quantity which is called the probability current density, psi star. All right, psi multiplied with the conjugate of the wave function. So you can see here, psi, the wave function, is equal to a e power I k x. The conjugate of this wave function would be a e power minus I k x. A conjugate of a complex number, you just take the imaginary number and then put an opposite sign or a negative sign just before that. So, for example, if I have a complex number, let's say x plus iy, its conjugate, which is represented with an asterisk or a star at the top, will become equal to x minus iy. X minus iy, on the other hand, will become equal to x plus iy again. The minus of minus becomes plus. So it's like that. So what you do is, when you multiply psi, the wave function, with its own conjugate and integrate it with respect to position between 2 points, let's say x1 and x2. I can see in the chat once. How does doing this mathematics principle not contradict physical laws like Heisenberg's uncertainty principle? On paper, we can extract position and momentum of a system from the wave function anytime, but in physical reality, all right, Aditya, are you there?
Yes, sir.
Uh, uh, these equations or these mathematical results that we are getting are completely in accordance with your physical laws like Heisenberg's uncertainty principle. What happens is, the example that you have given right now, that for example, the momentum was found to be an accurate value of h cross k. Now it is correct that if momentum is found to be accurate, the position cannot be found accurate, and that is why this wave equation that you can see here right now, this is the equation that we had used to find the momentum, right? This equation is of a free particle that can be anywhere at any given time, so its position cannot be found. Got it? These results are completely in accordance with all the principles. After considering all that only, these equations were created.
But this is only for a free particle, right? What if we take a particle which is not free?
If the particle is not free, then obviously the result will change because the wave function also changes. For example, if you take the particle and you put inside a box a confinement, all right, let's say of length L, the wave function again changes. It becomes root of 2 by L times sine of pi times x by L. You can solve this, is pretty easy using the applications of quantum mechanics. Now, when you try to find the value of momentum, it turns out to be zero.
Oh,
Why?
okay.
Because the position of the particle is confined. It is known, right? It will be anywhere between 0 and L.
Oh, so the maths doesn't allow it. Similar to physical reality.
Yes, maths will always be in accordance. So at such a level, understand that at such a level we cannot actually observe things, right? So whatever mathematics
Yeah.
we actually create has to be in accordance with the physical reality. This is a rule. This is a principle. This is called Bohr's correspondence principle.
Okay.
All right, you cannot create a mathematical what's it called equation which does not comply with what you actually observe in reality. Got it? We
Oh, okay.
strictly
Yes.
always consider the Bohr's correspondence principle before we give any result in quantum mechanics.
Yeah. Got it, sir. Thank you.
Got, got it? Sure, no?
Yes, sir. Yes, sir.
Okay, okay. So coming back here, please pay attention. So what happens here is that when you multiply the wave function of a material, I'll just erase this just a second. So when you multiply the wave function with its own conjugate and integrate it with position between 2 points, this gives you the probability of finding the particle between the 2 points, in this case x1 and x2. This is the first interpretation, very important interpretation. So using wave function, you can not only calculate the necessary information about the particle, you can also calculate every statistical information. Like what is the probability of finding the particle? You remember there was a question here. What was the probability of finding the particle in one of these boxes? You can find that as well using the wave function of the particle. Next, the second interpretation. How do we find out the result of an experiment to be accurate or not? What is the guarantee that the result is accurate? The simple concept is the probability of finding a result or to calculate the accuracy of the result depends again on the probability of finding the particle itself in that state. Now this is a little intensive, so what we'll do is we'll discuss this for a little bit of time. Let's say a particle is present in a certain state, a certain condition. Let's say that state is psi, a state or a condition of a particle. Now let's say you want to find out whether it is possible to find that same particle, whether it is possible to find the particle in another state, find in another state let's call it phi. So how will you find the probability of finding the particle in a state which is already present in state psi in another state which is phi? As an example, let's say I have a particle which is moving along the x-axis. Okay, so of course its momentum is along the x-axis. I know this to be true. So let's represent this with psi x. Okay. Let's say I want to find out whether the same particle is also traveling along the y-axis or not. So the question is, the particle traveling along the y-axis? Now, if the particle was traveling along the y-axis, its wave function would be psi y, isn't it so? The result or the answer to this question, or the probability of finding the particle which is already traveling along the x-axis, meaning it has the wave function psi x, to also be traveling along the y-axis, having the wave function psi y, is given by another mathematics. Take a look here. You take the original state psi x, and with this you multiply the conjugate of the state in question, psi y conjugate, and then you integrate it throughout space dx. This result is called the inner product, which is a very important topic in quantum mechanics. If you want to find the position, or you can say the state of a particle measured in one system and tested in another system, We are going to use inner product for our case. So let's say that we have a ball that is in blue color. So I'll represent the state with psi b or blue. Is it possible that the same ball can also have green color? Is it possible that the same ball is green as well? So what will we do? We'll take the original state, we'll write it down. We'll take the new state, which is psi g, and we'll take its conjugate, and then we'll integrate it throughout space, meaning throughout the boundaries, from, in this case, from minus infinity to infinity. Because if the particle exists, it will exist anywhere between minus 50 and infinity, right? With dx. All right, so this here is going to be the answer. Now let's say it is not possible at all. It is not possible that the ball which is present in blue color is also going to exist in green color. What will happen? The answer would become 0, because there is no such probability. If it is 100% guaranteed, if let's say the ball which is in blue color will also definitely be in green, the answer will become a 1. So this is the result of inner products. This is how you calculate the statistics of getting a result. Got it? So if let's say the original question, in a box there were 4 chambers, A, B, C, D. So to find out in which box or in which chamber is the ball present, is the particle present, you will take the wave function of the particle and you'll take the state equation or the wave function of the particle if it was in A or B or C or D. So let's say you want to find out what is the probability that the particle will be found in chamber A. So psi A star into psi, integrate with dx, and you will get the answer as 1 by 4, because you know the probability of finding it here was 1 by 4. Same thing with all. Understood? But if the particle was, let's say, in B, if the particle is already in B, and now you want to figure out if the particle is in B, can it still be at A? Can it still be in chamber A? The answer would become 0. Did you understand? Okay. Now there is a simple question. If we already find the particle at one state, why do we expect the particle to be found in another state? Because there are many systems and there are many, what's it called, cases in which a particle found in one state can also exist simultaneously in another state. And this is called the weirdness of quantum mechanics. I'll explain this to you with the help of an example. All right, this is an experiment that is conducted, an actual experiment that is conducted, which shows the multiplicity of these states. All right, which is the single photon interference. Now, I suppose all of you know what is meant by interference, isn't it so? When you have a coherent source and then you have two slits, then light passes through these two slits, and after that it starts to interfere with each other, and this results in an interference pattern. Now suppose that there is a single photon, all right, a single photon that is traveling here, and as it travels it can either pass through slit 1 or it can pass through slit 2. Can the photon pass through both the slits at the same time? Is it possible? For example, Vinayak, is it possible? If let's say I walk into a room with two doors. Is it possible that I enter through both the doors at the same time?
No, sir. You can go at
It's
least one.
only one, isn't it so? Now, this is actually true. So let's say if this is the slit A
Is this
and this
live?
is the slit B.
Hello?
Hello?
Is this live lecture?
Yes, yes, it is live only.
Huh?
Okay, take a look here. So you have A and B here, slit A and slit B. Then in that case, if the particle is present in the slit A, it can certainly not be found in slit B. In other words, the inner product of A and B definitely is zero. But what we actually observe is that even though there is only one single photon, there will still be an interference pattern. There is still going to be an interference pattern. Now, how do we explain this? Interference can be produced only if there is at least one photon in one state and at least another photon in the other state. So you need a minimum of two photons or you need one photon in each of these slits. Only then interference occurs. But how does interference occur in this case? It is because in quantum mechanics, the same particle can be found in multiple states at the same time. The same particle can be found in multiple states at the same time. It is not always possible, but in some cases it is possible. Nevertheless, the question of why do we have to find that, why do we have to figure out whether the particle is present in one state or the other, can be explained as such. Is this understood?
Hello, sir.
Yeah. Yes, Vinay.
Sir, that multidisciplinary characteristic, it's only in the mathematical state, or we can also observe in the physical reality?
We can actually observe this in the physical reality. This experiment that I had shown here is not a thought experiment. It is an actual experiment which is actually observed. Mathematically also it can be shown, but it is actually observed as well.
Yeah, sir, but I am still that
I know
it
this
is
is
like,
weird. This is called the weirdness of quantum mechanics for a reason. All right, this is actually observed. All right, and no matter how what's it called accurate your experiments are, you will always figure out that the photon still creates an interference pattern. Now, of course, you cannot observe the photon in both the slits at the same time. In 50% of the experiments, you will see the photon in slit B. 50% you will experience the photon in slit A. Why? Because again, mathematics cannot go against physical reality, Bohr's correspondence principle. But you will still see an interference pattern in every experiment.
sir, is it the effect of the observer if we didn't put
No,
any
it is
observer?
not. No, no, it is not observer's effect. Observer's effect is a very different thing. This is not observer's effect. This is just an uncertainty principle.
Thank you, sir. Thank you.
Okay. All right. So we are going to wrap this up with the last part here, a very important concept which all of you will be using. Whatever we have discussed here, students, is more than enough for you all to start studying quantum mechanics, by yourself as well, whether in your first year or final year, does not matter. These are what forms, or these are the basics, not just basics, these are the foundations of quantum mechanics completely. Of course, there are certain derivations and certain, what's it called, important mathematics and derivations that you have to figure out, and you can do that pretty easily. But this is what quantum mechanics actually means. Now, I'm going to end this session with explaining to you a little bit about what's it called, the wave functions, and how you can create a wave function and how you can actually what's it called, understand a wave function. A wave
Sir.
function, yeah.
So what is pound breaking strength, sir?
Say again.
Pound breaking strength. What is the meaning of that?
Pound breaking strength.
Yes.
Pound breaking strength has nothing to do with quantum mechanics.
No, because I've come across this meaning in mathematics I have come across, like, so I just wanted to know what it
No,
is.
that a pound breaking strength is a very different concept. It's about stress and strain. All right, it has nothing to do with quantum mechanics. All right, for example,
Okay.
let's say you have what's it called, a device, you can say a racket or something, whatever you want, any type of a device that is uh, using what's it called, weight as one of its forces. All right, then the value of the force, let's say for example, 1,000 pounds, 10,000 pounds, 100,000 pounds, or 500 kilograms and stuff like that. All right, that would be the limit, would be called a breaking strength.
Okay,
Got it? So that has nothing to do with
got
quantum
it.
mechanics. That's about stress and strain.
I
You
just
take a
thought it was a
stick,
part of that.
you take a, for example, that wooden ruler you remember that we used to get beaten from by our teachers when we were kids.
Yeah.
So what was the strength? What was the limit that would break that ruler? Breaking strength, breaking stress, you might call it as well. Okay.
Okay.
Okay. So
Thanks.
anyway, a wave function here is made of two important parts. There is one constant which is called an amplitude. The second part is a function of position and time. All right. A here is the amplitude. Amplitude. This is called the probability amplitude. Amplitude means what? The maximum value, right? So probability amplitude is the square root of the maximum probability of this given state. Understand one thing, we have shifted our concepts very completely. You remember in the beginning we were talking about the wave function being a packet of information, and then out of nowhere suddenly, and we all got transitioned into this, the wave function is now representing a state. So that's why the wave function is now called the state function as well. This was the result of the statistical interpretation. So the maximum probability of finding the particle in this state is called the probability amplitude. You remember the probability of the particle being found in one of the chambers was 1 by 4. So I was using the probability as 1 by, the amplitude as 1 by root 4. The square root of the maximum probability. Got it? Second, this function of space and time describes the distribution of the square root of probability in space and time. What do I mean by that? Let's see a very simple example here. Now suppose that there is this saucer. All of you know what a saucer is. And then there is a small ball which is moving in the saucer up and down, oscillating. Let's say from minus a to plus a. This is 0. This is your x-axis. This is your x-axis. So for example, let's say I ask you, where would you say the ball is to be found? If let's say I told you that you will get 5 lakh if you can guess exactly where the ball is found. Of course, it is not possible at all to accurately tell where the ball is present. But what would be your best guess? Aditya, what would be your best guess to find the location of the ball? Normally it would be 0
At the origin.
Zero.
at the origin, isn't it so? So the probability, it's not 100% guarantee that the ball will be at 0, but it's a probability or a higher probability that the ball is present at x equals to 0 as compared to this. So you can see this blue line, right? This is the graph of probability. This is probability. The maximum probability, as you can see, was 1. Of course, there is no probability that can be equal to 1 because that will be guarantee. We cannot guarantee where the ball is. Got it? This is another quantum mechanical system. You can see this here, this blue line is the result of psi into psi star. All right, psi into psi star. Now, if you are an expert in mathematics, you can figure out and you can say that the only function that will produce such a graph is something like a e power minus x square. Now, if you can just plot this graph, you will see that this is actually correct. I'll plot it and I'll show it to you. You can see that if I use the function, let's say of minus x power 2, look at the graph. Can you see this graph? This black line here? This is the graph. All right, so using probability distribution as well, we can find out the nature of the wave function. All right, so these two components of a wave function are very important. We first describe the probability amplitude, and then we describe the distribution of probability in space. Now, sometimes the probability can be influenced with time as well. For example, after some time in this case, what will happen? The probability would look like this. And let's say at the end of time, because of drag force, the graph will look like this. You can see a small spike. One of you had asked this question. The small spike present with probability equal to 1 because the particle will come to rest at this position. So this would be the statistical interpretation, and with this we would end the session. When we talk about quantum mechanics, students, we always talk about two very important concepts: understanding how to find the quantities associated with the particle, and understanding the statistical distribution of the particle as well as its informations. What is the probability that so and so is the momentum? What is the probability in that so and so is the position? All right, if you can cover these things, you will find quantum mechanics really very easy, and it becomes really very simple and very interesting, as a matter of fact, to take quantum mechanics above this level into a more in-depth and a more research oriented fashion. So that would be uh, the end of today's session. Back to you, Siddharth.
Thank you so much. I think we have, the last 5 minutes in case anybody else has any final questions.
Regarding the upcoming course, how much of particle physics are you going to cover?
Particle physics is actually not a part of this course. Particle physics is going to be a different course completely, which, because quantum mechanics is just particle physics comes much later. That's a specific specialization itself. So that there will be a different workshop on particle physics, but it will not be a part of the 3-day workshop. This is going to be more about the course content and the problem solving skills in quantum mechanics.
So we have a couple of questions. Are harmonic oscillators in 1D and 3D covered as well in the workshop?
Yes, of course. So quantum mechanics, applications of quantum mechanics includes simple harmonic oscillators. It's also going to include spherical symmetric potentials, the hydrogen atom and stuff like that.
Yeah, and I'm guessing it will definitely include infinite potential well and other things.
Yeah, that's just the beginning. That's the beginning.
Right,
Infinite
exactly.
potentials.
Yeah, so we'll post the link on Discord and Telegram as well, but we would like to personally mail it to you since we wanted to give out this link to participants of today's workshop. So you guys, if you can save that link or finish it off by tomorrow, the registration, that would be best. Are there any other questions for him regarding the session or related to what he taught? Okay. All right. So I don't think there are any other questions. So with that, we'll end today's workshop. So basically, just to give you guys a picture of Nakshatra's upcoming calendar. So the coming weekend, we have this quantum mechanics workshop, and immediately December 1st week, we'll be starting the classical mechanics course. So that will be 6 weeks long. And simultaneously, we'll be having a Python course as well. So if you guys want to, learn a bit of coding, you can register for the Python course. And people who are here, we have like a, kind of a special entrance into our research project that's kind of happening currently on Cepheid variable stars. So just look out on learn.nakshatra, and you can apply over there. It's just a Google form through the website.
हेलो मैम.
Yeah.
मैम स्क्रीन कोई दिख
Yes.
नहीं रही है.
Yes, my video is not on. Okay. All right. Yeah, we'll end here, guys. I'll just post one last time the link